Hi, scholars. It is Mrs. Gregerson. Just wanted to start us off on chapter 11, which is all about circles. Now, I want you to understand something about circles. This stuff, it is on the SAT. Standardized test. Geometry. ACT has lots of geometry on it, all different types. But on the SAT, for some reason, the geometry they love are circle problems, and they're normally thought of as higher level type problems. So if you can understand and do this chapter well and maintain it and review it, you'll do a good job. So supposedly, I think on Easter Monday, we're supposed to have a guest come in and teach class, and this is a long lesson, so I just didn't feel it was fair for her to try to cram a whole lesson in and then us try to catch up. So I thought I would do a quick review with you, make sure we have the correct terms and stuff when we're working with it, and then on Monday when she teaches, you guys can have a lot more hands-on and just being able to work with the lesson. So just thought it'd work out a little bit better. So today we're going to do a little bit of review, correcting some terminology, learn why we're learning this stuff, and then we're just going to do some problems. You do have a homework. It's a homework supplement, but really what I did is I pulled out the answers, I guess you could say, problems that are like that I'm teaching to you. I pulled them out of the homework assignment that will be due on Monday. So it makes your homework assignment shorter on Monday. Total of 6 problems due for me due on Monday. Does that make sense? So Monday night's homework will be longer, will be shorter, but also very short homework over the weekend. All right. So friends, let's do a quick review of what a circle is. Remember, a circle is a set of all points in a plane, the same distance from a point called the center. Now remember, we identify circles by their center point, and we also use the circle symbol to represent a circle. Remember, we had some other terms that we talked about. We talked about the interior of a circle is everything on the inside, and then all the points outside of the circle is the exterior. The circle itself are all those set of points. Now, we also know naturally about the diameter and also the radius at this point. Remember, the diameter goes through the center and it's a line segment whose endpoints are on the circle. And then we also have our radius, which is the line segment from the center point to any point on the circle. And then we have an infinite number of radii for each circle, but they're all the same length, which are going to be critical things that we do. Now, we have some terms that we want to make sure that we understand. And this is terms you probably have had before, but we're going to use a lot of it in this chapter. The first one is the term a chord, okay? A chord is a line segment whose endpoints lie on a circle. So with that, you would have line segment AB, okay? So here it starts and ends on the circle. Now I want you guys to think about a diameter, okay? A diameter goes through the center, but where are its endpoints? Its endpoints are on the circle. So think about a diameter is technically really a chord. And here's the other cool part. It's the longest chord for any circle. So a diameter is also a chord. So it's going to have length of line segments, all those other good stuff. All right. Now, the next one is like taking a chord and extending it. It's called a secant line. A secant is a line that literally goes through the circle. But think about it. It would contain a chord in it. So like just take a chord and then just keep on going outside of the circle. So in this case, in the diagram to the right, that's going to be line L. So a secant line, a secant is a line that contains a chord. It hits the circle at 2 spots. Is the way to think about it. And then one after that is we have what's called a tangent line. Now I want you to think what a tangent is. If you're telling a story and you're like, oh yeah, that reminds me, and then you start talking about something else, that's called a tangent of a story because you're going away from your original story. So a tangent line is a line that touches a circle at one spot. Okay, just touches it, or it looks like the circle is resting on it, and then it continually keeps on going. Now, tangent lines are actually really important. We use secant and the words tangent a lot when we're talking about it in calculus, and I'll talk about that in a moment. But remember, tangent, we're talking about a tangent line, and the diagram to the right, that is going to be line M. Now, that name of the point where when the tangent line intersects the circle is called the point of tangency, and that's actually really important. We're going to refer to that a lot in this section and a lot for this chapter. So point of tangency is really important, and that's actually a big term you use in calculus a lot. And so in this diagram, make sure we use a capital letter, right? It's going to be point C. Now let me explain why these terms are really important. When you get into calculus, you're going to get like funky graphs that you're going to have. And we're going to ask you to ask questions like as math teachers, and there's a lot of reasons why, that you're going to be looking for the area underneath the curve. And so we need to approximate it. So a lot of times to start approximate, they use a secant line, and then they draw that secant line in, and then all of a sudden, guess what? I'm going to make a trapezoid. So we have secant lines where they're going to intersect the curve in two spots, and I could have a secant line right here because it intersects at two spots, and so on. So we could work with secant lines a lot, but that's not the only thing they work with in calculus. In calculus, our big thing is called a derivative, which gives us the slope of the tangent line of a curve at a given point. So the cool thing is when I talk about tangent lines, if I'm talking about that point, that is the slope of the line, tangent line. And so we talk about tangents, and I can have a tangent here, and I can have a tangent here. And it really, we talk about the different points of tangency with our curve. So you're going to see that in your future in calculus and stuff. And so when you're talking about limits and things as well. Okay, sidebar why you need to know that. Now let's look at this diagram and let's label all of its parts. I like this. It says identify each line or segment that intersects circle L. So we want to know exactly what's going on. So first thing, so we have talked about line segments. Do you guys agree with me that I can have some chords? Okay, so you agree with me that segment KM, remember how we name line segments to the endpoints, and the segment bar at the top is a chord. Is there any other chords in this diagram? And I hope you also said segment JM is also a chord. Be right here would be your chord. And then we had KM, which is also known as our what? You're right, that's also known as a diameter. Perfect. All right, now what do we have next that's intersecting the circle? Do you guys agree with me that we have a secant line? Oops, I can't spell secant though. All right. So our secant is going to be line JM. Remember, chord JM is a line segment, but if it keeps on going, that becomes a secant line, and that'd be line JM. Pretty simple so far. Now, do I have a tangent? Yeah. A tangent line is a line that intersects a circle at exactly one point, and that would be line M. Now, please don't do this. I've had people use bad notation and go, oh, that's line segment HM. Friends, in order to have a line named by points, don't you have to have 2 points? So be very careful. That is just line M, who has a point of tangency at point H. Does that make sense? So the point of tangency would be point H. Now, those aren't the only things drawn here. Do you guys realize there's a couple other things drawn? Do you guys agree with me that we actually have the radii of the circle, correct? I have segment KL, segment JL, and segment LM that are all radii of the circle. So those are all ones that you should know. So make sure you're able to identify those. Make sure you're able to work with all of those. Okay, some other review that we had, some terms that we talked about. Things you know, congruent circles. Can circles be the same size and shape? Exactly. So congruent circles, remember, are going to have congruent radii. Very important that you know. Look, you even use the congruency symbol with circles. Okay, so it'd be circle A is congruent to circle B. Now, only if that's the case, if you have the fact that the radii are congruent. Now notice, guys, that's written as a biconditional, so remember it goes both ways, but pretty important. All right, we did talk about this before. We talked about concentric circles. Remember, concentric circles, we talked about the target symbol is this, are completeness circles that have the same center. So like, how would you describe that? You'd have to say the large circle with the center A, or in this case we'd say the red circle, and then there would be like the blue circle. So it's really important that we know the different terminology with these. All right, So now we're actually going to talk a little bit more. We're still going to talk about tangency, but we're going to specifically refer to it with circles. Okay. Now, when two circles intersect and they intersect at only one point, that one point is still called a tangent point or a point of tangency. So those circles are going to be called tangent circles. They intersect at exactly one spot. So let's write this down. So we have our tangent circles. Now, I hope you guys are kind of catching on to the phrase. Tangency means you intersect at how many points? 1 point, okay? So when it's two circles intersect at exactly 1 point, we have tangent circles. There's two different types. We have what are called eternally tangent circles. And that's when you have one circle inside the other and they intersect at your point of tangency at one spot, okay? And then we have what are called externally tangent circles, where they intersect each other, but they're both outside of each other. The only thing they have in common is that point of tangency. So one's external of the other. But internally tangent, there's literally a smaller circle inside the other one, which is really huge. Okay, so some new terminology. We had tangent circles, concentric circles, and congruent circles. Pretty basic and easy to get. So let's look at this next diagram, and you will have a couple of problems, like one or two problems like this, and I want you to think about it through. It says, find the length of each radius, identify the point of tangency, and write the equation of the tangent line at this point. Wow, that was goofy. I can't read. All right, so find the length of each radius. So guys, what's the length of our radius right here? Right? So the radius of circle S is going to be what? What's its length? Yeah, that's going to be 3/2, or we could say 1.5, correct? So that's the length of the radius for circle S. So what's the radius for circle R? Well, for circle R, all right, so we're looking at the radius of circle R, so that is going to be the radius is going to have a length of 2. Now, we have to identify the point of tangency, right, where the two circles are intersecting. All right, first of all, their point of tangency right here is at -2, 0, but make sure, let's use this correct terminology. Are those externally tangent circles, or are they internally tangent circles? Do you guys agree with me? Those we considered externally tangent because they just touched each other. One is not inside of the other. Great. Now we're supposed to find the tangent line. All right, so the equation of the tangent line. Now guys, yes, you have to remember equations of lines. Okay, that is very important that you remember. Now, first of all, do you guys agree with me? My tangent line would be right here between the two. Well, what type of line is that, my friends? Is that a horizontal line? So it has a slope of 0. So remember, we have a shortcut way. If we have a horizontal line, it is whatever the y variable is. So that would be y is equal to 0. Now, or we can use the idea that the slope would be 0 and our point we'd use is -2, 0, and then we could use point slope form, correct? Well, then all you'd have to put in is y plus 2 is equal to 0 times the quantity. Oops, I put that in the wrong spot. Let's try that again. So y minus 0 equals 0 times the quantity x plus 2 when we plug it in. And 0 times anything is what, my friends? 0. But if I asked you for the equation of line, I would take either one of those. Actually, is very valid. But remember, you have a horizontal line, so it's y equals. If I had a vertical line, it would be x equals whatever your x coordinate is. So just kind of remember those. All right, some other terms. We talk about tangent lines, and we have, when we have two circles, we have what are called a common tangent line. If a line is tangent to one or more circle, it is a common tangent because it's in common with more than one thing. So you have two different types. You have an external common tangent when it's just touching like on the outside. So line L and line M would be considered external common tangents. However, we also have what are called the common internal tangents, and those are tangent lines who go between the two circles. So think about that. If I have externally tangent circles and I draw the tangent line between them, that would be actually called common internal tangent. So that tangent line is a common internal tangent because it's between the two circles. All right, now why are these important? Well, let me explain something. A lot of times when you are working in geometry, they like to draw a tangent between two circles. And if you notice, I'm drawing my radii to the point of tangencies. Now, if I was drawing this ultra well, let's see if I could redraw this middle one here and be ultra well. Do you guys agree with me? With this blue line, don't I make two triangles? They end up being right triangles. You're going to find that out in just a moment. And they also end up being similar to each other. So we end up using similarity when we work with these. Or I can draw the radii into each of these, and I'm going to end up drawing some diagrams I can use to solve for missing parts. So we're going to use those a lot today. All right, so first theorem about tangent lines you have to know, and this is one of the most important theorems of this chapter you have to keep memorized, okay, is the following. If a line is tangent to a circle, all right, so if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So here's my point of tangency, point B, right? If I draw the radius from my center A to there, guess what type of angle you're always going to get? It's always going to be perpendicular. So I want to show you this diagram again. Remember, I drew the radius here, and I drew the radius here to the point of tangency. What type of angles are being drawn? Now when I connect those two centers of the circles together, and I have those, guys, do you agree with me with the vertical angles? Those two triangles are similar. And it's because of the rule here that if I draw my radius to the point of tangency, I will always, 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 always form a right angle. You should always draw it in. All right, so let me give you an example of applying this. It's kind of fun. Okay, so we have right here early space travel, and this is a very like simplified version of this. Okay, this is not like hidden figures type calculations they're doing, but they use those type of things. It says early in its flight, the Apollo 11 spacecraft orbited Earth at an altitude of 120 miles. So where's the altitude of that? That'd be right here. That's 120 right there, my friends. Okay, and then it asked, what was the distance from the spacecraft to Earth's horizon rounded to the nearest mile? So I want to know what this is right here. But I want to know it to the nearest mile. Now, here's a few things you need to know. What is that 4,000 talking about? Guys, that 4,000 miles is going to be the radius of our Earth. Okay? So with that, when you're working with it, what would be my whole distance right there? Do you guys agree with me? That would be 4,120 miles. Now, guys, that means I know this part of the right triangle because remember my radius to the point of tangency is a right angle. So isn't that the hypotenuse? Do I know the length of a radius? Yes. Which is a leg. Can I solve for the other leg of this right triangle? And if I know two sides of a right triangle, how do I find the missing side? You're correct, the Pythagorean theorem. So we're going to have leg squared plus leg squared equals hypotenuse squared. All right, now this said round to the nearest mile. So guys, I'm going to let the calculator do a lot of work. So first things first, you guys agree with me, x squared is really 4,120 squared minus 4,000 squared. I'm just going to keep it simple on ourselves. Then I'm going to end up taking the square root of both sides. So x is really plus or minus the square root of, and I think if you punch this into your calculator, double check me on this one because I'm doing this without my calculator. I'm doing this for my notes, and you know that could be totally wrong, guys. So should be 974,400, and this would be like squared. probably miles here. Okay, if I take the square root of that, what do I get to the nearest mile? And that would be about 987 miles. Now, what did I do? Remember, I used the fact I formed a right triangle. And do we know how to work with right triangles, guys? Are we brilliant with that? Yes, yes, we are. We can totally get those. All right, so here's another example of what you'd be expected to know. And this is what is very specific example. This would be like what you saw up here, common tangents that look like this, okay, is what we're working with. But here's a few things you need to remember. First of all, it says in the diagram, line XY is tangent to circles O and P. So XY, and it says ZY here. It should be, let's change that to an X. Let's make this easy on ourselves. That says XY, and it should be ZY. Okay. But we'll change X to our diagram. It's tangent to both. But what do I have drawn for circle O and circle P? I have a right angle drawn. Right? Because the radius to the point of tangency is a right angle. Now, I want to know x, which is the distance, and this is a lot of times will be written out like this, the distance between the two centers. All right? So I want to know the distance between the centers of the two circles. Well, if I have the radius drawn, my friends, I have to have some way drawn it. Now, someone looks like, do you guys agree with me? It looks like I have a trapezoid. That's great, but trapezoid's not going to help me solve for x in this case, but I can use stuff that I know to help me out. Now, guys, if you do it the way that I show you here, which means you might have to rewatch this back when you're working on your homework, you will get it right. When you do this, I'm going to do a divide and conquer kind of idea here. I am going to start at the radius of the smaller circle and draw a line segment, and you know this is not going to be straight, guys, so you got to use your imagination here. That's parallel to my common tangent. If I draw so it's parallel to the common tangent, I'm going to use the fact that those would all form right angles. Now, if you notice that, do you guys agree with me that this right here, and I'm going to draw it in blue, so hopefully you can see it a little bit better, that triangle right there is a right triangle? What do I know about this right triangle? Would you guys agree with me that I formed a rectangle as the other portion of it, so I knew its opposite sides are the same, so I know that this segment and this segment are the same. They're both 25. Now, you guys also agree with me that this line segment and this one would have to be the same. That would be 9 from here to here, which leaves this little segment, or that little leg of that right triangle, to be 3. So basically I just formed, and this is not drawn to scale whatsoever, a leg of 3, a leg of 25, finally, just so I can get from the distance between O and P. But what I'm doing is I'm creating a right triangle, and if I know two sides of a right triangle, guys, how are we going to solve for the missing side? That's right, Pythagorean theorem. So we're going to go leg squared plus leg squared equals hypotenuse squared. So we get 9 plus, what's 25 squared? Isn't that 625? Is that right, my friends? Equals x squared. And so that ends up being 634 is equal to x squared. And then we take the square root of both sides. It's plus or minus, but we are talking length. And x is going to equal, my friends, the square root of 634. I'm looking at this, guys, and I don't think there is any perfect square numbers that come out of it. I could be wrong. I'm just saying that right now. But for right now, you should always leave it in simplest form. But our answer is going to be the square root of 634. Now, here's the other thing you need to know. I could have done the exact same process if I had a tangent line drawn below, and I would actually get the same type of ideas. So just remember, just because I have it set up here on top doesn't mean it can't happen on the bottom, and that's going to hint to help you on your homework supplement. All right, so let's try another one of these. Okay, again, I don't know why it says XY for every one of these. It is so ZY, but for some reason I have an X, so I'll just get past it, is tangent to both circles again. So the radius to the point of tangency, what do we always form, my friends? right angles. Now, this time I'm not looking for the distance between the centers. I've been given the distance between the centers. Okay, I know the distance between the two is 7. But the cool part here, I'm still going to go from the center of the smallest circle and draw it so it's parallel to my common tangent. Let's see if I can get any better. All right, parallel to the common tangent, and I get a right angle right here. The reason I'm doing that, again, I'm dividing that into a rectangle and a right triangle, correct? Because that would be like this if I draw them so they're parallel. So the cool thing is, if xy is x, that means this side opposite of that rectangle is x. I can use the idea of the radius is 2 right here. If this is 2 right here, from here to here on that one is also going to be 2. So I'm going to change that to 2, which means this little segment right there is 1. So again, can I solve using the right triangle with this, correct? We're going to go, again, leg squared plus leg squared equals hypotenuse squared. So I get 1 plus x squared is equal to 49. Subtract 1. X squared is equal to 48. Take the square root of that. Guys, what's x going to be? Should be 4 root 3. So the cool part is, same type of process, just know what part am I looking for. Am I looking for maybe the length of that segment, xy, which is part of the common tangent, or am I looking for like the distance between the centers? Guys, you have like 3 problems like this on your homework supplement. So if you're stuck, re-watch. Okay, so make sure you re-watch. Re-watch if stuck. On homework supplement, which is the worksheet that we have. Okay, guys, now that's where we're going to end on our notes. Hopefully that helps you guys get started on your notes. You can see how this would take a long time if we're going to do this on Monday. Make sure it's 6 questions. Follow the homework supplement. You guys should be good. All right, guys, thank you for listening. Hope you have a great and blessed Easter.